In this video, we are going to look at the electron configuration practice sheet. So on this sheet, we are working to write the electron configuration, the noble gas or shorthand electron configuration, and then to determine the number of energy levels, number of total electrons, and number of valence electrons for the element. And then finally, we will draw the Bohr model. So here, down at the bottom, we have our electron configuration chart, which will help us when writing our electron configuration. So let's start out with chlorine. So the first step in writing electron configuration is to figure out the total number of electrons that the element has. So to do that, we can look at where it is in the periodic table. So chlorine is element number 17. And so we need to write out the electron configuration up until chlorine, or element up until electron number 17. So we'll start out and we just read our periodic table from left to right. And we start out in the first energy level, so that indicates that we write a 1. And then we start out in the S block. This red part is the S block. And we're going to go 1, 2 into the S block. So we're going to fill that first S orbital and write 1s2. The next electrons will go into the 2s orbital, and that will also be filled. We're going all the way across the 2s block of the periodic table, so 2s2. Then if we keep reading from left to right, we hit the p block. And so the next part of our electron configuration is going to be 2p, and we're going to go all 6 of the way across the p block. So the next piece will be 2p6. And then we've hit the end of our periodic table. We move back over to the left, and now we are in energy level 3, and we're back in the S block, in the red S block. And we'll go all the way across the S block, so we'll write 3s2. If we keep reading left to right, we now enter the 3p block, but chlorine is only part way through the p block. It's element 1, 2, 3, 4, 5. So we only need to put 5 of the 6 total electrons that our 3p orbital could hold. So instead of writing 3p6, we will put 3p5 to indicate that chlorine only needs 5 more electrons to get to the total of 17. And of course, we can check our work by going back and adding up the total number of electrons we put in our electron configuration. And of course, 2 plus 2 plus 6 plus 2 plus 5 gives us a total of 17 electrons, which is indeed the correct number of electrons for chlorine, as chlorine is element number 17 on the periodic table. Now, to write the noble gas or the shorthand electron configuration, we first need to find the noble gas that comes before chlorine. So the noble gases are over here in group 18 of the periodic table. And we need the noble gas that comes before chlorine, so not argon. Argon's after, it's number 18. We need to go all the way back across until we find the noble gas that comes before fluorine, which of course is neon, number 10. So we'll put neon in brackets. And that tells us that the first part of our electron configuration, the first 10 electrons, are going to be the exact same configuration as neon. So we only need to write the portion of our electron configuration that's after neon. So we wrote neon down, now we're going to keep reading, we're going to go back left to right, so we'll write 3s2. And then we'll finish our configuration off with our 3p5. So you can see how this is a much shorter way of writing our electron configuration. This shorthand notation allows us to eliminate all this first part, and we can shorten that down to just say neon, and then we can add the piece of the electron configuration that is after neon. Now we want to determine the number of energy levels. So remember, our pieces of electron configuration, the energy level is shown out front, is the coefficient. So we have energy level 1, energy level 2, energy level 3, and that's it. So there are 3 total energy levels here. 3 total energy levels. We already figured out the total number of electrons because we put that number of electrons in our configuration. We know that 2 plus 2 plus 6 plus 2 plus 5 gives us 17 total electrons. And then the last thing is to figure out the number of valence electrons. So we need to figure out the valence shell. The valence shell is equal to our number of energy levels. So our valence shell is going to be energy level 3. So to figure out the number of valence electrons, all we need to do is look for all the electrons in energy level 3. So I see a 3 here in this s orbital. And there are 2 electrons in that orbital. And then I see a 3 here, and there are 5 electrons in this p orbital. So our total number of valence electrons is going to be 2 plus 5 for a total of 7 valence electrons. And this makes sense because we know that chlorine is in group 17 of the periodic table, so we expected it to have 7 valence electrons. So that is yet another indication that we wrote our configuration correctly. The last piece of this is to draw a Bohr model. And we're going to simplify our Bohr model a little bit. Instead of drawing dots for every single electron, we're just going to put numbers indicating the number of electrons in each energy level. So I'm going to start out by putting my chemical symbol in the middle, chlorine, and I'm going to put the same number of rings as I have energy levels. So this would be 3. So 1 ring, 2 rings, and 3 rings. So now we've drawn our 3 energy levels for our Bohr model. So the next step is to figure out how many electrons need to go on each of these energy levels. And to figure that out, we'll just look back at our electron configuration. So in energy level 1, the first ring of our Bohr model, we're just looking at the pieces of our configuration that start with a 1. And I only see this first piece, the 1s2 starts with a 1. And we're just looking for the number of electrons in that first energy level. So in that first energy level, there are only 2 electrons. Just these 2 electrons are in that first energy level. So I'm going to put a 2 on the first ring of my Bohr model to indicate that there are 2 electrons on that first ring. Now in energy level 2, I'm looking for the bits of my electron configuration that start with a 2. And so I see 2s2, and I also see 2p6. And that's all I see. So we're going to add the 2 plus 6. So in my second energy level, we have a total of 8 electrons. So I'm going to put an 8 to indicate that there are 8 electrons on that second energy level. And you could draw 8 dots and draw 2 dots if you wanted to, but I just think it's a little bit easier to just write the numbers. Either way is fine. Now for energy level 3, we'll look for the bits of our configuration that start with 3. I see 3s2, 3p5. So 2 plus 5, we already added up to equal 7. So we'll put 7 on that valence energy level to show that there are 7 valence electrons. Moving on. Next we have germanium. So the first step here is to find germanium on the periodic table. And so if we're looking at our periodic table, germanium is number 32 right here. So we know we need to fit in 32 electrons in our configuration. And we are just going to start at the top and keep writing electron configuration until we get to germanium on our periodic table. Starting with 1 and then the s block, so 1s, and we're going all the way through, so 1s2, 1s2, then going down to energy level 2, 2s2. Now we go over to the p block, 2p6. Now down to energy level 3, s2, 3s2, then 3p6, and then 4s2. And then our next segment is in the D block. And we know that the D block bumps back in energy level. So this isn't 4d10, this is 3d. 3d, and we're going all the way across the D block. And so we know that 10 electrons can fit in those d orbitals. Or if you don't remember that, just count across. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That reminds you that 10 electrons can fit in those d orbitals. So we'll write 3d10. And then the last piece of our electron configuration is in the p block. We're back in energy level 4. So this is 4p, and we're just going 2 elements into the p block. Electrons 31 and 32 go in the 4p set of orbitals. 4p2 is our final piece of our electron configuration. Now that was a lot of writing, so let's go ahead and shorten this down and write the noble gas notation. We're looking for the noble gas that comes before germanium, and so we're going backwards on our periodic table. So we're going back from element 32 all the way back, going back up to energy level 3, and so our noble gas that comes before germanium is argon, Ar. So we'll put Ar in brackets. And that takes care of the first 18 electrons in germanium's electron configuration. So now we just need to write the part of the configuration that comes after argon. And so I'm going to go ahead and erase this so we can redo this portion of our electron configuration here. So it makes it a little easier for us. And so we need to write this 4s2 part. And then we need to write 3d10. And then last but not least, we'll end with our 4p2. So we were able to cut down this electron configuration quite significantly. Looking at our number of energy levels, I see energy level 1, energy level 2, energy level 3, and then energy level 4. So 4 energy levels in total. Our total number of electrons, we could just add up our superscripts, but also germanium we know should have 32 total electrons by looking at that atomic number. And then the number of valence electrons. To figure this out, we need to look back at our electron configuration and look at energy level 4. I see energy level 4 here and here. And the number of electrons is going to be 2 plus the 2 in the p orbitals. So the s electrons plus those p electrons. So 2 plus 2 gives us 4 valence electrons. Last but not least, let's draw our Bohr model. So for germanium, we know that we need 4 energy levels. So I'm going to start with the chemical symbol, Ge. And then I'm going to go ahead and put 4 rings. 1, 2, 3, and 4. Not the best artist here. And now let's start with our valence shell this time, because we already counted up the number of valence electrons we have. We know that our 4th energy level is going to have 4 electrons. So in our outermost shell, our valence shell, I will put a 4 to indicate there are 4 electrons in that shell. Let's do energy level 3 next. So if we look back at our electron configuration, we find everything with a 3 out front. Don't forget the D block. Okay, so we have 10 electrons plus 6 electrons plus 2 electrons. So 10 plus 6 plus 2 gives us 18 total electrons in that 3rd energy level. Then let's look at energy level 2. We'll do that in yellow. Energy level 2, I see 2s2 and 2p6. So if we add 2 plus 6 together, 2 plus 6 gives us 8 electrons in that 2nd energy level. And then last but not least, energy level 1. Energy level 1, we just have this 1s2, so just 2 electrons in energy level 1. And there is our Bohr model for germanium. On to copper. And we'll go a little faster through this one. Hopefully we're getting better at this. So copper is element 29, right here on the periodic table, element 29. So we know that the total number of electrons should be 29. So I'm going to go ahead and record the total number of electrons this time. Do this a little bit in a different order. Before I write my electron configuration, we'll record the total number of electrons. And now, even though it doesn't ask for it, I'm going to start by writing out the whole electron configuration for copper. So starting out with 1s2, 1s2, and then 2s2, and then 2p6, and then 3s2, and then 3p6, next 4s2, and then we're going to end in the D block this time. Remember, it's 3D, and we are 3D, and we're the second to last one, so this is the 9th element in the D block. So we'll end in 3D9. To shorten this notation, we'll look for the noble gas that comes before copper, and that is argon, number 18. So we'll put argon in brackets, and we'll write the portion of the configuration that comes after argon. So that would be this 4s2 part, and then that 3d9 portion of our configuration. The number of energy levels, well, we went all the way down to energy level 4. So there are 4 total energy levels in this configuration. And the number of valence electrons, we're just looking at the portion of the configuration that starts with a 4, and that's this 4s2. So that means that there are only 2 valence electrons here. 2 valence electrons. Let's draw our Bohr model. For copper, the chemical symbol is Cu. And once again, we need 4 rings. 1, 2, 3, and 4. Whoops, that wasn't my best ring. Let's maybe redo that one. Draw that again. 4. Right, 4 rings. We'll start with the valence shell again, because I think that's a little easier. We know our valence shell has just 2 electrons, so we'll put a 2 in the energy level number 4. Next, we'll go back to energy level number 3. So we have 3s2, 3p6, and 3d9. So we need to add these numbers up. 2 plus 6 plus 9, so that gives us 17 electrons in that 3rd energy level. 17 electrons there. Next, let's do energy level 2. We have 2s2, whoops, wrong marker that time. Try that again. We have 2s2 and 2p6. So that's 2 electrons plus 6 electrons for 8 in energy level 2. And then last but not least, we have energy level number 1. And we just have this 1s2, so there'll be 2 electrons in energy level 1. Next we have molybdenum. So molybdenum is symbol MO. It's element number 42 on the periodic table, right here. So this will be a slightly longer configuration than we've written before, but it's no big deal. We know that this just follows the pattern of the periodic table. We'll start with 1s2, and then 2s2, 1s2, 2s2, and then we know 2p6, and then 3s2, then 3p6, 4s2, and then we go to 3d10, then 4p6, and then we go back down to 5s2. Whoops, I wrote the wrong number there. Let's go back. 5s2. And then we're ending in the 4D block. And we're 1, 2, 3, 4 elements in. So we're ending with 4D4. There's our full electron configuration. Let's shorten that because that is sure a lot of writing. Okay, so the noble gas that comes before molybdenum, well, let's find that. So molybdenum's right here. If we need to go back on the periodic table, molybdenum's 42. The noble gas that comes before it is krypton. So we're going to put krypton in brackets. Brackets, Kr. And now we'll do the part of the configuration that is left after krypton. So that would be 5s2 and 4d4. 4d4. That was a lot shorter than our full electron configuration. Now for our energy levels, the highest number that we got down to on energy levels is 5, and you can check that in your electron configuration. The highest number is 5, so we have 5 energy levels. We know molybdenum has 42 electrons in its configuration, so 42 total electrons. And then for valence electrons, we need to look at that highest energy level number 5. So looking at energy level number 5, I only see one piece of our configuration with a 5 out front. That's this 5s2 portion. So that means that there are only 2 valence electrons in molybdenum. 2 valence electrons. Last but not least, let's draw our Bohr model. So we'll get our pen out. Okay, molybdenum's chemical symbol is Mo, and this time we need 5 rings. I'm going to have to be really neat here. 1, 2, 3, 4, and last but not least, 5 rings in our Bohr model. We know our number of valence electrons already. It's 2. We already figured that out, so we'll start with the outermost ring, and we'll work our way in. So energy level number 4, we have 4s2, we have 4p6, and we have 4d4. So 2 plus 6 plus 4, that will give us a total, 2 plus 6 plus 4, of 12 electrons in the 4th energy level. Then we go to energy level number 3. We'll do that in green. We have 3s2, 3p6, and 3d10. So if we add up the 2 plus 6 plus 10, that gives us a total of 18 electrons. I guess we use green for the 5th energy level too, but that's okay. We'll do energy level number 2 in blue, 2s2 and 2p6. 2 plus 6 gives us 8 electrons in that 2nd energy level. And then last but not least, we have energy level number 1 with just those 2s electrons. There's our Bohr model. Next, we have magnesium. Magnesium is element number 12 on the periodic table. Thank goodness, a shorter electron configuration to write out. This one's very easy compared to the previous ones. So we'll write 1s2, 2s2, 2p6. We'll start there. 1s2, 2s2, 2p6, and then 3s2. And that's the end of our electron configuration. Way shorter than our last one. Our noble gas notation, we're going back from magnesium, so we're moving backwards to neon. So neon goes in brackets here. And then we just write the part that comes after neon, which is this 3s2 part. Whew, that was way easier. So number of energy levels here, well, I see 1s, 2s, and 3s. So our highest energy level is 3. We know magnesium has 12 total electrons from its atomic number. And then for number of valence electrons, this one's a lot easier because we only have 3 energy levels. So we just have 2 valence electrons. Both those valence electrons are in the 3s orbital. So 2 valence electrons. Our Bohr model should be easier to draw too this time because we only need 3 rings. Magnesium is Mg. 1 ring. 2 rings, and 3 rings. Our valence shell, we already said, has 2 electrons in it. Then we can do our second energy level. We have 2s2 and 2p6. 2 plus 6 gives us 8. And then in our first energy level, we just have this one s2 part, so we know there are just 2 electrons in that first energy level. Last but not least, we have argon. So argon's configuration, we need to go all the way up to electron number 18. We'll start by writing 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 3s2 comes next, 3s2, and then 3p6. So because argon is a noble gas, its electron configuration is already perfect, and we can summarize its electron configuration as just the noble gas in brackets. Number of energy levels, well, argon has 1, 2, 3 energy levels. We can tell this from our configuration because the highest number out front, the highest coefficient, is a 3. We know argon has 18 total electrons, or we could add up all of our coefficients to figure that out. And then as for valence electrons, it's a noble gas, so it's going to have a perfect number of valence electrons, meaning has a full s and p orbital for a total of 8, meaning that it already has an octet. So now let's draw our Bohr model for our perfect noble gas, argon. Argon has 3 energy levels. We know in its valence shell it has 8 electrons. In its second energy level, we have the s and the p electrons, so 2 plus 6 gives us 8 electrons there as well. And then in its first energy level, we just have those 1s electrons, and we know that that can only be 2 electrons.